Would you think I show you the time travel picture when I talk about storage? I do it because I think there is something we can learn from the past. There's something very important happening right now. And there is something really interesting happening in the future from now on. That's why I wanted to take you on a half-hour time travel. And I'll start back in 1966, which coincidentally is my birth year. So now you know that when you work in storage in IBM, that means you're normal gray beard and all that stuff. Okay. In 1966, a colleague from us invented this thing here, DRAM. So the invention was, let's try and store data in a volatile fashion. DRAM means dynamic or volatile, also means anything that they store in here is not kept and doesn't stay there. You have to refresh all this. But that opens the path to much smaller cells, much cheaper storage, much simplified production mechanisms, and the price that you have nowadays for DRAM, and everybody of us is carrying this around in the pocket. Now, a couple of years later, this thing happened here. That was Dov Froman from Intel, and he had another idea. Let's store data in a way that it's not erasable, not at all, except through really hard measures like you illuminate it with Röntgen beams or with ultraviolet beams or, well, these kind of things. And that was the first EEPROM. And if you were born in 66 or a couple of years later, most likely you have seen EEPROMs, you've played with them, you've burned them. If you're born in the 80s, you don't know this. But it was a very important cornerstone in the technology because this one, the first one with a small open glass field, opened the path to the second one, which was the one that you could erase and reprogram. So electrically erasable programmable ROM, EEPROM. And that changed the industry because since that time, we can afford to write banana software. You know what that is? Banana software? It writes at the customer, right? So, and we all carry this around in our pockets. It's all banana software because this software is not yet 100% finished. There is security holes which are going to be found within the next month. And there is unhappy clients which would want to have something more. And all this will happen, will go into the software and will be flashed on your device into an EEPROM. And that is the birth time of that option. Without that, before that, anything that was manufactured had to be done and ready, 100% secured before you could send it out. It's an incredible cornerstone in the industry. It has changed our whole life so dramatically, and nobody really sees that. This thing here. And nowadays, 2010s and follow-ups, we still have the same technology. Now it's called flash chips, flash drives. It is the same, only it looks like it was readable and writable randomly, and you don't see that, in fact, underneath there's a process that asynchronously deletes stuff and does garbage collection. But it is there. And you can feel this process when you write a lot to a flash device very quickly. After a while, you would see that it slows down because in the back end, it can't cope with all the deletion processes. So there's a whole lot of work to be done in the back end. And still, the base technology is the same. 2015 is also a cornerstone because an important thing changes. Maybe one back. From here to here, we followed Moore's law. We've densified the cells. We've increased the output of the process. And the price was getting lower by factors. And now we've hit the kind of wall. Because what we see is between 20 and 16 nanometers of cell size. If we go smaller, we have so many induced errors that anything that we gain from now on, we have to spend on error correction. It's just no use going any lower. The more we go below 20 nanometers, the more we have to spend in gigabytes for error correction. And that is really a limit. And everybody was angry to see that limit and was, nobody knew what to do then. Now we have something. This here is a planar wafer, which means the cells are all aligned in a two-dimensional surface, and it looks like a bungalow. If you want to have more rooms in a bungalow, you have to have smaller rooms, which is the problem. These small rooms become uncomfortable and data is forgotten. And this is the new world since this year, three-dimensional technology, which means that now if you want more rooms, the chase is on who can build more stories. Now we build skyscrapers in the chip. So you don't see that. It's inside the surface. Okay? And that is the principle here of putting, in fact, a layer of transistors on a layer of transistors on a layer of transistors. Now, that looks like three. And the reality is that when you take pictures of these things, we are already at 16. And there's lab demonstrators that go to 32. And there is good ideas how to go to 64 layers, which also divides the price by 64. So the next years we will see some gold rush, like with the hard disk drives in the years 2000, when Java was invented. Without the cheap storage, nobody would have afforded Java, really. And we'll see how the industry reacts to this very cheap, compared to the past, very cheap, very quick storage, which is going to happen. And that's really sure that it is going to happen. Right now, the process is still expensive, so the output is expensive because the yield is not good. But industry has shown that this is going to be solved. In 2011, this is, by the way, from our internal journal that we have in our intranet. It's called W3. And in 2011, we had a project with the company Micron to launch 3D chip making. And that was the initial idea to realize RAM, three-dimensional RAM. And now, 4 years later, they have it also for flash. And we say, great, this is the company we want to partner with. This is also the company we want to sell technology to, but also purchase chips from. And these chips, we are now implanting the latest generation of our flash system. And there's something special in the flash system because it's not like the storage devices that we used to have. And the storage devices were all built for disks. And while we started putting flash in there, we built it this way here. So flash was in a small package, in a 3.5 or 2.5 inch package, and it did look like a disk. It's what is called an SSD, a solid-state device. While everything is solid-state here, we don't call these modules SSD anymore because they don't look like disks. They don't understand commands like move your head to the sector 0 or give me your boot sector or, these things. They don't understand things like scrubbing. They don't understand nothing from the world we know. They're not compatible backwards with the world. So they're not built to be a replacement for something. What we earn instead is we don't have the protocols here, the SAS protocol, the SATA protocol, the PCIe protocol, all the things that go in between. We skip all this, and we get the thing really quick and pretty dense. When you look at it, 5.7 terabyte, the size, the real size of it it's like a tie. Well, Olaf doesn't have a tie, but anyway, it's maybe 2 times, not more. It's extremely dense. Now, what can we do with it? We have the dense, very fast storage. It's a perfect storage for analytics, but we see that whenever we attach it to some server, the process of getting data to the storage or from the storage always involves different stages, which count up to an amount of approximately 20,000 lines of code. And any line of code that is in the middle is one too much. Okay, what can you do with it? Well, if you want to network your data, you will have to keep this, whatever technology that should be. But if that data is something that is networked from a data perspective, you have to keep this. If the data is only for this consumer here, then there's something new which is called KP, and it's reducing the 20,000 lines of code to 500, and the timing approximately identical way. So the timing is matches the division of lines of code. How does it work? It works by using an interface that was initially designed for the supercomputers, and the power-based supercomputers are not good at math, because the power is a RISC processor. It's a processor that doesn't have math capabilities. So power processors always said, whenever there's a math operation, we put the math operation on a coprocessor. And you all know the coprocessor companies. NVIDIA is a very famous one. They earn a lot of their money on mathematical coprocessors, most of which are used in graphics, gaming, right? They are mathematical coprocessors anyway. And this interface is used normally to attach the processor with the coprocessor. So it's memory mapping. And we're now memory mapping our processors to the storage base. And that is very quick. Now, what effect does that have? It looks like something that we call nearline RAM. It is almost RAM. It's not as fast, still a magnitude in between. It's not volatile, but it's much faster than anything we had until now when it came to network storage. So we can use it as a replacement for in-memory NoSQL. I think you all know these things, the different ways of building NoSQL in memory. This one particular, the one that you see here, would replace 24 x86 servers approximately with a RAM base of, say, 1 terabyte per x86 server. So this is the size that we would be able to match with that solution. But now it comes an energy play. If you're interested in low energy, and not so much in standardization on one single platform, and this is the way to go. It can be very economic. And this is how it looks when it's readily done. The usability of it, the major use cases, it's running with Big Redis. Big Redis is a variant of Redis that understands these two different flavors of RAM, the real one and the nearline RAM. And it's a big key value store that is enabled with analytical capabilities, the statistics, the hyperlog log calculation, and so on. That is all already in there. And it's now becoming very popular in gaming, but also anywhere where you would use hash tables or catalogs. Or, the biggest catalogs we have are genomics catalogs, I think. So a very interesting path, completely outside of what we thought the world would be, x86 and software, and very dense. Now, staying with media, what's the cheapest storage media in 2020? So let's extrapolate. Will it be flash? We don't know. We don't know whether there is going to be a way to go beyond 64 layers or 128 layers. There's still some headroom. Now, the cheapest media is still tape. Incredible. Yes, and it has so much headroom. This is an experiment from the Zurich labs. The Zurich labs are not in Zurich. I think you're all aware. They are in Rüschlikon, across the Zürichsee. Last year, 154 terabyte on one single cartridge. And the trick is here to shindle the storage. That means when you've written one track, the next track will overwrite the previous one, 90%. You just keep 10%. You just keep the amount that you need to be able to read it. That's all you need. Anyway, a tape is not random overwrite. Guess what? Now the first disks have come to the market. I think Hitachi 8 and 10 terabyte, which use exactly this technique. These disks are normal random overwrite disks. They need to write at the end always, and then there must be some garbage collection mechanisms inside. So everybody goes this direction. But this is not the end. The end is this one, 220 terabyte. At least that is the end as we see it right now. So that's the maximum we can push out of this experiment. It's one cartridge, this size, standard length, with 220 terabyte on it. Unfortunately, it still has to be pulled out. So the access time would be something between 30 seconds and a minute until you're at the data. What's it good for? It's good for all the data that most likely you need to put somewhere, but you're not going to read anytime soon. So all the legal data, all the protection backups, not the ones that you keep for logical restores, the first generation, but the previous generations that you keep for disaster recovery, for instance. Anything that you do not need to read unless there's really big disaster. That's what you put here. Idle data, stale data, all this stuff. 10 years, keeping data 10 years. So this works by adjusting the heads very precisely to where the tape is. The maximum run out of the head versus tape. Remember, the tape does not touch the head. They are loosely coupled. So the head is mounted on a servo, and it will follow the tape. Maximum run out is 5 nanometers, which is 1/100th of the wavelength of light, which is tiny, tiny, tiny. And then you get to these capacities. Now the market is not ready to accept that right now. The market is at 10 terabytes per cartridge, so we're 20 times in front of the market, 22 times. It's really plenty of confidence in the roadmap. And when you look at these different roadmaps, 3D Flash with 30 layers, 30 times ahead of the market. Well, okay, Flash is more expensive right now. And now the last one, the disk technology demonstrators, they're barely at 2 times what you can do now. That means within very few years from now on, the disks will feel very expensive compared to the new options that you will have right now. So the industry is changing completely. And we see that happening in the big industries already. Maybe you've seen it in your industry. Disks for fast operations are disappearing. And as it looks, even the disks for slow operations are going to be under a strong price pressure. There's still one thing that is really a perfect argument for the disk and for the tape, which is bit stability. Nothing is as stable as a tape or a disk. And we'll have some hard time with the electronic storage to get there. The question I'm getting quite often is, can't we push our data to the cloud? So that the cloud is cheap, and we want to push it outside, so that's available somewhere else, and somebody cares about us. Can cloud storage be even cheaper? Yes, it can, although they're using the same media. Okay, the media are the same. The cost economies are elsewhere. It's first, of course, economy of scale, and it's economy of cooling. This is the new Facebook data center in Luleå, northern polar circle in Sweden. They built it there not because most Facebook users are in northern Sweden, but because cooling comes for free. And at that scale, this is a big argument, big benefit. And as you know, Facebook is a synchronization app, so you're not interested in real-time access, and therefore we don't care where the thing is, really. And that is maybe one of the important parts when you consider cloud as a storage media. Bandwidth upload is important to notice. Bandwidth for download is also an important part. You need to know these. There's companies that offer you cloud storage for free upload, but when you want to restore anything, then you have to pay. And it's an interesting model. Okay? You have to know whether the download, the one that you never use, is fast enough for you. Latency should not be a topic. If it is, then you have the wrong solution. One of the big problems that we're going to see is that with cloud solutions, it's very hard to migrate out of one into another, especially if you have a petabyte or two stored at cloud XYZ, and now you say, I'll just stop my contracts and I start contracts with somebody else, and now how much time do I need to pull the 2 petabytes off here and put them there? And there's no standard for that, there's no agreement, there's no nothing. We shall see how that works. Okay. Now, there's only one solution I know of that needs real-time interactivity on the cloud. And that's a bit apart from what I showed you. That's the last thing I'm showing. It's a toy called Cognitoy. It's called, company is Elemental Path. The toy Cognitoy uses Watson technology, and Watson technology is just too expensive and too big to put it in a small toy. So it's a toy that is cloud-enabled, and it needs real-time connectivity. So watch this one. Didn't think about audio.
Hi, my name is Lily. Four. What is the speed of light?
The speed of light is 186,000 miles per second. Can you count to six?
1, 2, 3, 4, 5, 6. Tell me a knock-knock joke.
Knock, knock.
Who's there? Letter 2.
It is freezing outside.
My favorite color is orange.
Okay, I'll try to remember. Your favorite color is orange.
Do you play the alligator? Tell me a story.
We make a story together.
Good job. Keep it here. If it was below $100, would you buy it for your kids? Huh? Well, the good news is below $100. It's $99. It's crowdfunding, and IBM is the biggest part in the crowd that is funding that new toy. And the problem is it's only in English, because the whole Watson technology has been built on understanding of English language and culture. It does not yet understand Swiss German. And I think Swiss German is the last language that will be on the list, unfortunately. Why I'm showing you this is there was one or two important sentences in this video. Don't know if you catch them.
Hi, my name is Lily. My favorite color is orange.
Okay, I'll try to remember. Your favorite color is orange.
So, you seen what happens there? It's private data. It's private data that is not delivered as a document. So there is no metadata to support that it's private data. And when these kids grow up, they would look like this, I think, in their business lives. They will have plenty of tools that they talk to, and the tools are organizing their lives. For some of us who are using Siri or equivalent, it's already a little bit like this, but this is really the stone age of electronic interaction with a device that understands you and that organizes your life. Now, this thing here, I don't like appointments after 18 o'clock. Is that a private data or is that public? There's nothing to sustain that. So the privacy discussion will be a big one on these solutions, because these systems will have to learn, just like we learned, what in which culture is considered private information and what is public information. If you have children in the kindergarten, you know what I'm talking about. You have? Anyone? No? No? The teachers in the kindergarten know your whole life. Okay, thanks for taking it. That was it.
Let's take 3 questions.
Are you investigating ways to mark information as private inside of the storage, so that even if I get access to the storage, I cannot read everything?
I think the easiest way is the encryption way. So the knowledge that information is private has to come from the source, and if the source does encrypt that piece of information, then it is considered private. And there is no easy additional path to tell the system consider this information as private for him without encrypting. Unfortunately, encrypting breaks a couple of things, like you cannot deduplicate anything that is encrypted. You cannot compress anything that is encrypted. You cannot thin provision anything that is encrypted, because the zeros should be encrypted as well. So encryption is expensive.
Anybody else?
Those cartridges you write 10 times over sequentially. When you read them, can you read all 10 tracks at once?
We read 28 tracks at once. We always write 28 tracks and read 128 tracks. And we can read while we write it. Also, there's enough read heads and write heads on the small device that we can do all this in parallel. But they are all adjusted, so we only need one servo adjustment. And the read tracks are much narrower than the last written track. The last written track still has the full width of the coil, and the read tracks are very tiny. This is what we are optimizing right now. Yes, question.
What do you think about quantum computing and storage?
Well, there's been some recent new interest in quantum computing, but I think we will have, it's going to be a long time before quantum computing gets into our everyday lives. Reason being is that I believe the specialties of quantum computing are not anywhere in what I've been showing here. They are in reverse engineering encryption. This is what quantum computers are really good for. Reverse engineering encryption is going to be a big threat for all of us, I believe, including Bitcoin, by the way. So this is where I think we're going to see them at first, and not in anything that has to do with storing information or even understanding human interaction.